Chemistry, this is Lesson 1, the basic atom. These are the slides that were presented in class, and now you have them on a video that you can view anytime. So electrical force is the single most important factor in all of chemistry. The key point about electrical force is positive attracts negative and negative attracts positive. Positive repels, pushes away positive, and negative repels, pushes away negative. And you're going to see that basic principle appear almost every day in this class. An element is pure matter that cannot be divided into simpler substances. An atom is the smallest piece of an element. When you cut an element as far as you can, you have an atom of that element. There are 90 naturally occurring elements plus about another 28 that were created by scientists in laboratories. All matter in the universe is made of these 90 elements. Below are 5 naturally occurring elements. Carbon, of which graphite is one type, and that's what's in your pencil. Diamond is another type of carbon. Carbon is also coal, which is used to burn for fuel. Gold. They've known about gold for thousands of years, but they didn't understand until the last couple of hundred years the concept that it was an element, that it was a pure substance. Neon. Neon is a gas. It's used for a number of things. It's a noble gas, and it's used for, among other things, neon lights. Uranium. Uranium is the largest natural element in the universe. It's very radioactive, which means its nucleus falls apart very easily, and it's used for nuclear energy. Finally, mercury. Mercury is one of only 2 elements that's liquid at room temperature. It's a very toxic substance, and it is also so dense that a steel ball will float on top of liquid mercury. Just as the 26 letters of the English alphabet can be arranged to make millions of words, the 90 elements can be arranged and combined to make millions of different substances called compounds. A compound is a substance containing 2 or more elements. There are up to 50 million different chemical substances in the universe. Water, consisting of the elements hydrogen and oxygen, is the most common compound on Earth. The periodic table is a list of all elements in the universe. The periodic table is the centerpiece of the study of chemistry. What's amazing about this chart that you're looking at is it includes every element in the universe. How we know that, I'll talk to you about later. But every element in the universe is on this chart right here. Dimitri Mendeleev is credited with creating the periodic table. He did much of his work by laying out cards while riding trains around Russia. He didn't discover every element that you see on there. He didn't identify them, but where he found gaps, he predicted a certain element would exist, and in fact, it did turn up. The 2 main divisions are the metals, the metals, alkali, alkaline earth transition, and other metals. So those are the ones you see basically on the left 3/4 of the periodic table are those metals there. Now, even though they take up most of the periodic table, they are not a majority of the mass of the universe in terms of elements. Now, on the upper right-hand corner are the nonmetals. These nonmetals are the nonmetals, halogens, and noble gases. Your body is made up almost entirely of nonmetals, and so that little upper right-hand corner of the periodic table is where all the elements are that make up your body. The metalloids is that light green kind of diagonal section there, and it's kind of a border between the metals and the nonmetals and the metals. We don't really talk much about the metalloids. It has characteristics of both metals and nonmetals. Now, the first 2 columns and the last 6 columns are important in our study of chemistry, and we're going to spend most of our time talking about elements there. So that would be the group 1A, 2A, 3A, 4A, all the way up to 8A. There's 8 columns there, and we'll talk quite a bit about those. Those have a special place in chemistry. The transition metals in the middle, we'll talk about them, but they're not quite as important to our discussion of basic chemistry. Down at the bottom, the lanthanide and actinide series are not important at all, and we won't be talking about those. In about 400 BC, a Greek named Democritus developed the idea that there was a smallest piece of matter that could not be further divided. The Greek word atomos means indivisible, cannot be divided. The smallest piece of an element is called an atom. Now back then they didn't have the science to really prove this. There were some Greeks that thought, no, you could cut, if you had a piece of gold, you could cut it in half, take a piece of that, cut it in half, take a piece of that, cut it in half, and at least in principle you could cut it in half forever. What Democritus was saying is no. You keep cutting that piece of gold in half and cutting it in half, cutting it in half, you'll eventually get to a smallest piece of gold, which you cannot cut any further. In about 1800, English chemist John Dalton developed his atomic theory, describing atoms and how they combine to form compounds. 1. All elements are composed of indivisible atoms. Indivisible means cannot be divided. 2. Atoms of the same element are identical. Atoms of one element are different from those of another element. 3. Atoms of different elements can combine in whole number ratios. That means 1, 2, 3, 4, not 1.5, 2 3/4, or anything like that. In whole number ratios to form compounds. Compounds are combinations of two or more elements. And 4, chemical reactions are when atoms join, separate, or are rearranged. Atoms of one element cannot be changed into another element. The following are some notes concerning Dalton's 4 principles, and some corrections that were made later on. First, all elements are composed of indivisible atoms. Dalton developed these 4 postulates 100 years before the discovery of protons, neutrons, and electrons, which will be discussed. Dalton is correct that atoms cannot be divided into simpler substances. 2. Atoms of the same element are identical. Atoms of one element are different from those of another element. Dalton did not know of the concept of ions and isotopes, which will be discussed later. The following are some notes concerning Dalton's 4 principles. Number 3. Atoms of different elements can combine in whole number ratios to form compounds, combinations of 2 or more elements. This is completely correct. An atom cannot be divided, and this is why it's possible to have H2O but not H1.50. And number 4, chemical reactions are when atoms join, separate, or are rearranged. Atoms of one element cannot be changed into another element. The first sentence is completely correct. Rearrangements of atoms is really the definition of chemical reactions. Atoms, however, can be changed into other elements. This occurs during nuclear reactions which involve changes in the nucleus. An atom is the smallest piece of an element there is. If you cut an atom of gold or iron in half, you will no longer have gold or iron. An atom consists of 3 parts: protons, positive charges; neutrons, no charge; and electrons, negative charges. So let's look at the basic anatomy of an atom, what it's made up of. There's a center called the nucleus. That's the center of the atom. And it consists of, well, let's go to this. Orbitals, also called shells, are energy levels where electrons move around the nucleus. Now inside the nucleus you have protons. Those are the positively charged particles. And neutrons. Those are the neutral or no charge particles. And then flying around the outside of the nucleus are electrons. Those are the negatively charged particles that circle the nucleus. So what holds the electrons close to the atom are the protons. The protons and electrons attract each other. The electrons have enough energy so that they won't just fly into the nucleus, but they will stay within a certain distance because the protons keep them there. So a valence orbital is the outer orbital of an atom. Because helium, and this is a helium atom, has only one orbital, this is the valence orbital. Valence electrons are the electrons in the valence orbital. It is the valence electrons that form chemical bonds, to be discussed later. So the valence electrons, that's where the action is. That's where the frontline foot soldiers are. Those are the electrons that come in contact with other atoms, and that's when chemical bonds are formed. So this word valence electron, you'll be hearing almost every day in this class. It's really the most, one of the most important concepts of the structure of an atom. What holds the protons in the nucleus? They're both positively charged, after all. Shouldn't they repel each other and push apart and fly out? There's something called the strong nuclear force. And when you can get the protons close enough together, they'll hook onto each other. And neutrons, which have no charge, so neutrons don't repel protons, also have these hooks. So the neutrons hook onto the protons hook onto each other, and they hold together. And that's called the strong nuclear force. So that's much stronger than what's called the electromagnetic force that causes the protons to repel each other. So let's look at these particles one at a time. A proton is the positively charged part of an atom. You don't need to understand what positive means other than it's the opposite of negative. In other words, positive, negative, they could have called it the yes and no particle, the red and blue particle, the up and down particle. It just means it's opposite. A proton has a mass, as you see there, you don't need to know that number, which is 1,836 times more massive than an electron. So just understand, the electrons which are flying around the nucleus are very small and light. So just kind of remember that. If they're flying around, they have to be very small and very light. So they're much smaller and much lighter than a proton. A proton has a charge you see there, you don't need to know that number, which is a number we will rarely use. More commonly, we assign a charge of +1 and a mass of 1 atomic mass unit to a proton. So an atomic mass unit is simply defined as the mass or the weight of a proton. And the charge we simply call a +1. It's a positive charge. One proton has a charge of +1. It's just by definition, that's how they decided it would be. Protons contain the strong nuclear force which holds them together in the nucleus against the repulsion of the electromagnetic force. Now let's look at the electron. An electron is the negatively charged part of an atom. An electron has a negative charge equal and opposite to that of a proton, which is that number you see there. I'll read that number one time, but you don't have to know it. It's 1.602 times 10 to the minus 19th coulombs. A coulomb is a measure of electrical charge. An electron has a mass, you can see there, it's very small, and if you go back to the last slide and compare it, it's much, much smaller than the proton. An electron moves outside the nucleus in specified energy levels called orbitals. And one other point to make about the electron, it's much smaller and much lighter than a proton, but it has the same charge, just opposite. Proton +1, electron -1. Finally, a neutron is a part of an atom that has no charge. In the simplest sense, a neutron is made up of a proton and an electron, which neutralize each other. They cancel each other out, basically, and give the neutron no charge. A neutron has a mass, you can see it there, it's just about the same as a proton. We treat it as though it's exactly the same as a proton for our purposes. This is slightly more than the mass of a proton, but not exactly equal to the mass of a proton and an electron added together. Again, that's not important. What's important is we're going to treat the mass of a neutron as being the same as the mass of a proton. In chemistry, we assign a charge of 0 and a mass of 1 to the neutron. So it has the same mass as a proton, but it has no charge. Neutrons contain the strong nuclear force which holds protons together in the nucleus against the electromagnetic force. The electromagnetic force is the one that wants to push the two positive charges apart. Chemical reactions create new substances by rearranging atoms into new compounds through a chemical reaction. An example is 2H2, that would be read 2 hydrogen molecules, and we'll define molecules later, plus 1 oxygen molecule produces 2 molecules of H2O, which, as you know, is water. Water is comprised of 2 atoms of hydrogen and 1 atom of oxygen. A chemical change occurs when the atoms combine to form a structure called a molecule. Because water is made up of more than one different kind of element, it is referred to as a compound. So here's what's called a particulate diagram. So you see what a hydrogen molecule is it's two hydrogen atoms put together. Hydrogen always likes to pair up with another hydrogen. It always does that. You'll never find hydrogen just by itself in a gas form. Gas meaning like floats in the atmosphere. So what it's saying there is you have two hydrogen atoms, you have two hydrogen molecules. Each molecule has two atoms. Then you move to the right, you see O2. That means you have two atoms of oxygen which also like to travel in pairs. So that forms an oxygen molecule. And what they do is they break apart by smashing into each other, and they recombine to form two water molecules. So a water molecule is H2O, as you can see over there on the right, and there's two of them. So if you count, you have 4 hydrogen atoms on the left and 4 hydrogen atoms on the right. You have 2 oxygen atoms on the left and 2 oxygen atoms on the right. So you cannot create or destroy elements or atoms in a chemical reaction. You have to end up with as many after the reaction is over as before the reaction started. Chemical reactions create new substances by rearranging atoms into new compounds through a chemical reaction, and there's the example. Water is made of 2 hydrogen atoms and 1 oxygen atom to form a new substance called water, H2O. The way water reacts with your body is totally different than the way pure oxygen and pure hydrogen react with your body. So there we see the same diagram. So the point is simply, you could not drink some liquid hydrogen and liquid oxygen and have it affect your body the same as water. Water, it has a unique structure that your body knows how to process, which is different than just hydrogen molecules and oxygen molecules separately. Physical changes determine whether a particular substance is solid, liquid, or gas form. These are called states or phases of matter. There are 3 states of matter: solid, liquid, and gas. Solids, the molecules are held firmly together. In the case of water, we call this ice. Liquids, the molecules touch each other but can move around one another, so liquid water splashes around. Finally, gas. The molecules have enough energy to separate from each other and move upward against gravity. So that's what we would call either evaporated water, or if you're boiling it on the stove, it would be steam. The molecules have enough energy to break away from the liquid water and go up into the atmosphere. A nuclear reaction is one where the number of protons or neutrons is changed. So something in the nucleus changes. Not the electrons, but the nucleus, the protons or neutrons. Number of protons changes. Elements are defined by the number of protons. I'm going to say that again because that is incredibly important to remember in this class. Elements are defined by the number of protons. So for example, hydrogen has 1 proton. If the atom doesn't have 1 proton, it's not hydrogen. Helium has 2 protons. If it's a different number of protons, it's not helium. It must have 2 protons to be helium. So elements are defined by the number of protons, not the number of neutrons or electrons. So if a proton is added or removed from an oxygen atom, the atom will no longer be oxygen. Number of neutrons change. The number of neutrons in 2 atoms of the same element can be different. These are called isotopes. Carbon has 6 protons. Most carbon atoms also have 6 neutrons, but there are some that have 7 or even 8 neutrons. These different atoms are isotopes of carbon. So the element is still carbon. As long as it has 6 protons, it's carbon, but it can have different numbers of neutrons. So how does that make the element different, or the atoms different? It just makes some heavier and some lighter. They're still carbon, they still react the same way chemically, but some are heavier and some are lighter. And that takes care of our very first lesson. So we've had this some time ago in class, but I wanted to get that up for you so you can review it for your test. And go ahead and just watch the video, take whatever notes you think you want to take, and that will get you ready for the test. So we'll see you on the next lesson.